Well, hello everybody. So, today we have come to the second class on the mass transfer processes. Now, just to recollect what we had discussed in the previous class, we had mentioned that we are primarily concerned with interphase mass transfer, where between two phases there are some particular components which get transferred from say phase A to phase B, where phase B can be created from phase A either by the addition of some form of energy or pressure reduction, or there can be an addition of an external phase. Whatever be the case, moment there are two phases, the two phases they come in contact and mass transfer occurs between these two phases till the two phases attain equilibrium. And at that time I had also mentioned that therefore, in this particular case of interface mass transfer, what is important? It is important that the two phases are far removed from equilibrium if we want the interface mass transfer to go on, and this differentiates the interface mass transfer from the mass transfer which occurs inside any particular phase. Inside a phase, the mass transfer occurs due to concentration difference of any particular component between 2 points in that particular phase. And in this particular case, what we find that the mass transfer occurs because the composition of the transferable component is such that the two phases are not in equilibrium, or in other words, the chemical potential of the two phases are not the same, right. So, therefore, whether mass transfer is going to occur or not, that is going to depend on the value of the chemical potential corresponding to the two phases, and therefore, the compositions which correspond to equality of chemical potential signifies that the two phases are in equilibrium with respect to the transferable component. Now, here I would just like to mention that equilibrium and steady state, there is a basic difference. What is the difference? Under equilibrium conditions, we consider that in the entire phase A and in the entire phase B, the concentrations are uniform throughout. In phase A and phase B, the concentrations may be different, but in the entire phase A and in the entire phase B, the compositions they have to be they are the same. And in steady state, what do we assume? We assume that inside the phase A, at every particular point, the composition does not change with time, but the compositions may vary from point to point. So, therefore, this means that under equilibrium composition, the composition within a particular phase, it neither varies with time nor with any axial position, while under steady state conditions, the composition, or for that matter all thermodynamic properties, they are invariant with time, but they vary from location to location, which implies that equilibrium is comprises or encompasses steady state operations, but steady state operations are not equilibrium operations. So, therefore, if we therefore, the basic operations which we had discussed in the last class, and the operations which we will be discussing in much more details in the subsequent classes, for example, distillation, absorption, adsorption, extraction, etc., etc. So, all these operations, they are basically interface mass transfer operations, where the second phase is either created by addition of energy, primarily in the form of heat, or maybe by pressure reduction, and or by addition of a second phase. Whatever be the condition, there has to be two phases and there has to be some components which will be transferred from phase 1 to phase 2. Now, when will this transfer occur? This transfer will occur, as I had mentioned in the last class, when the chemical potential of that particular component, say I, that is in the phase say alpha, that is not equal to the chemical potential of the component in the beta phase. Only when this happens, then your the ith component will diffuse from the alpha phase to the beta phase, provided mu I alpha is greater than mu I beta, and if the reverse thing happens, then the ith component will move from the beta phase to the alpha phase. So, therefore, the rate of mass transfer and how much amount of mass transfer is going to occur, that is going to depend on how much different mu I of component I in the alpha phase is different as compared to mu of component I in the beta phase. And therefore, the composition of I corresponding to mu I alpha and the composition of I corresponding to mu I at beta, these two particular compositions, they have to correspond to mu I alpha equals to mu I beta for the mass transfer to stop or to not happen. What I mean to say is that suppose I say that in alpha phase I denote the composition as xi, right. So, xi corresponding to mu I alpha, and for the beta phase, suppose I assume that the composition is denoted by yi. So, yi corresponding to mu I beta. Now, these two compositions are important, and mass transfer will stop when mu I alpha will be equal to mu I beta. So, for this particular condition, whatever xi and yi compositions are there, they are known as the equilibrium compositions. It can always happen that xi and yi are equal, yet mass transfer is occurring, because even when xi and yi are equal, we find that mu I alpha is not equal to mu I beta. And it can also happen that yi is much higher than xi, yet we find mass transfer occurs of component I from alpha to the beta phase. This is because even if yi is higher, it is lower compared to the equilibrium composition of yi, which is in equilibrium with xi. So, therefore, what I would like to say is, it is very important to consider the equilibrium conditions and then to relate the compositions corresponding to equilibrium, or rather this is known as the generation of equilibrium data. That is something very important in order to understand mass transfer, interface mass transfer operations. So, quite naturally, when we will be dealing with distillation, vapor liquid equilibrium is going to be important when the vapor and liquid corresponds to the same set of components. When it is absorption, definitely here also vapor liquid or gas liquid equilibrium is important, but in this cases naturally the gas and the liquid phase, they do not comprise of all the components are not the same, or in other words, the gas phase comprises of several non-condensable components. Same things applies for stripping as well. For adsorption and leaching, definitely it is the solid liquid and the solid gas equilibrium which is important, and for extraction it is the equilibrium between two liquid phases which are not miscible with each other to the total extent. That means, the two liquid phases, they may have some miscibility and they usually have some miscibility with one another, but they definitely form two distinct immiscible phases, and there is one component or more than one component which diffuses from one liquid phase to the other liquid phase, just because the mu of that component I in liquid 1 say is not equal to mu of that component in the second liquid phase. So, therefore, how do we express the concentration of the component I, where I assume that the component I is the component which is being transferred from one phase to the other. In that particular case, how do we express the composition of component I? Now, the most common way of expressing is definitely the mole fraction, or in other words, mole fraction means moles of I in say some particular phase divided by total moles of the mixture. So, if I assume that Xi refers to the composition say in the liquid phase, then in that case it is moles of I in the liquid phase divided by total moles of mixture in the liquid phase. Likewise, Yi by convention generally refers to the mole fraction of component I in the vapor phase. If there are two liquids, then it refers to the component, rather the composition of component I in the phase which is extracting, or rather this we call it as the solvent. Okay. So, for most of the cases we find that conventionally we usually express the species concentration either in terms of mole fraction of the species I or with respect to some property which is proportional to the mole fraction. For example, in the gas phase, generally what we do, we use the, I will just change the color of the pen for your convenience. Yeah, for example, in the gas phase, normally we use the partial pressure of the species I in the vapor phase or the gas phase. And for the liquid phase, what we do? We can either use the mole fraction, or else we can express the liquid phase composition in terms of the concentration. This concentration can be weight per weight, maybe milligrams per gram or parts per million weight or any other weight per weight. It can be volume per volume, or it can be weight per volume also, and we can also have some particular other type of units, for example, normality, molarity and etc., etc. We can also have molality, we can also express concentration in these particular terms as well. And for the solid phase, by convention, at least for this particular course, what we would like to do is, we would like to refer to the concentration in the solid phase in terms of Q or in terms of Qi. So, what I would like to conclude is, when we will be dealing with liquid phase compositions, it will either be, if we are referring to in terms of the mole fractions, then generally in the liquid phase the composition is expressed by Xi, and the composition in the gas phase or the vapor phase, that is expressed in terms of Yi. Usually in the vapor or the gas phase, usually we find, we will be discussing later, then rather than Yi, it is often convenient to express it in terms of the partial pressure. And in the liquid phase, rather than a mole fraction, we often use any particular concentration unit. It can also be, say for example, the color intensity of a dye solution which is related to the concentration. It can be a measure of absorbance or conductance, etc. Okay. So, for distillation and absorption, generally we deal with distillation, it is Yi versus Xi. For absorption, it is all sometimes preferable to use Pi versus Xi. For extraction, we quite often we can use something like the Yi versus Xi, where Yi refers to the composition of the component I in the extract phase or the phase where the component has been extracted, and Xi refers to the raffinate phase or the phase which is remaining from the feed after the component has been extracted. And when we are dealing with adsorption or maybe leaching, for those particular cases we generally represent it as Qi versus Ci. This is for adsorption or leaching. And when we are dealing with gas liquid adsorption, under that case we can also represent it as Qi versus Pi. So, therefore, these are the different ways. This was for gas solid cases and this was for liquid solid cases, this was for liquid cases, this was for vapor liquid equilibrium. So, therefore, the equilibrium data, it can be represented in terms of graphs or tables. We can also have some equations to develop the relationships between x, y or pi, xi and etc., whatever we have mentioned. Just to understand equilibrium a little, definitely this is not a mass transfer, a thermodynamics class. So, therefore, I will not be going into the details of equilibrium, but just to as a recap of the thermodynamics course that you have already done. So, therefore, I would just like to represent or just like to recall a few things that we had already discussed in your thermodynamics class. Whenever we represent equilibrium, let me be very specific, we are talking about chemical equilibrium, right. I will just mention, and this is not a part of this particular course, nevertheless, that thermodynamic equilibrium is satisfied when we have a combination of mechanical equilibrium, thermal equilibrium and chemical equilibrium, or in other words, delta P equals to 0, delta T equals to 0, or T is the same in all the phases, and in this case it is usually referred to as the Gibbs free energy delta G equals to 0, which automatically implies that mu of each component, suppose there are two phases alpha and beta, then mu of each component should be equal in the two phases. So, therefore, just let us recollect that how to express, because see, if we know how to express mu in terms of composition, temperature and pressure, then in that case, suppose there is any particular way of finding out mu of component I under the conditions of temperature and pressure existing in phase alpha, or in other words, what I mean to say that if there is a way of expressing mu I in the alpha phase and in terms of temperature and pressure, and there is a way of expressing mu of the same component I in the beta phase as a function of temperature and pressure, if we have those particular relationships, then in that case using those relationships we can find out mu I alpha, we can find out mu I beta, and if we find that mu I alpha is greater than mu I beta, I moves from alpha to beta phase. If mu I alpha is less than mu I beta, then I moves from the beta to the alpha phase. Now, you must be recollecting that for a pure component d mu it is equal to minus S dt plus V dP. So, therefore, at constant temperature if we take, then in that case d mu equals to V dP. So, what we find is that if we really want to find out mu under any particular temperature and pressure, then this particular equation, it has to be integrated from some particular standard state to the temperature and pressure conditions which are existing in the alpha phase. So, accordingly this equation also has to be integrated from some particular standard state to the pressure, since temperature is constant, right. Now, the point is that if we have to use this equation and find out the mu of component I in the alpha phase or maybe component I in the beta phase using this particular relationship, then we need to know mu at some particular standard states, isn't it? We need to know mu, say suppose this is mu I 0 and this corresponds to mu, right. So, we need to know mu I at some particular standard state, only with respect to that we can find out mu under the conditions that we want. Now, this I will tell you, this is one particular very important problem of thermodynamics, is that more than the equations, it is very difficult to understand that most of the equations which express properties in terms of measurable properties, they are as differential equations or difference equations. So, therefore, if we want to find out the absolute value of any property, we need to know the value of that property under some particular standard conditions. Now, mu itself is an abstract quantity. So, how to find out the value of mu at any particular standard state? We just do not have any clue on that. Now, whenever we become so clueless, we immediately resort to one particular thing, that is the ideal gas state. Because ideal gas state, since it is based on the kinetic theory of gases, so therefore, for the ideal gas state, most of the equations, they are quite well defined. So, denoting the ideal gas state with the superscript 0, what do we find? We find out that in the ideal gas state, d mu 0, if I write, denoting the condition of the ideal gas state, that is definitely equals to V dP, and for the ideal gas state, this V is nothing but RT by P dP. So, therefore, and this is nothing but RT d ln P. So, therefore, we find that for an ideal gas, we know that the change in mu in going from one state to the other is related to the change in the ln P. So, from there it was felt, there is a very famous scientist G. N. Lewis, who felt that why not retain this particular same expression for mu for any other substance other than the ideal gas, merely by replacing P with F, and keeping in mind that this F becomes equal to P when this particular substance behaves as an ideal gas. Or in other words, what was felt is that for any particular substance, why do not we write this as integral RT d ln F, where we know that F becomes equal to P under the ideal gas state. And when does any particular substance behave as an ideal gas? When the pressure is very low. So, therefore, what does this mean? This means that what we have done in this process is, we have simply replaced this function d mu with RT d ln F, knowing fully well that F becomes equals to P as P tends to 0, right. So, therefore, the defining equation for fugacity, the purpose of doing this is that we did not know the lower limit or the standard state based on which mu should be calculated, but if we replace this equation in the ideal gas equation, if we relate this particular P with F, then we know the value of F under some particular standard state which corresponds to the ideal gas situation. So, therefore, what is the defining equation for fugacity? The defining equation for fugacity is written in this particular form, that so, what we do, if we want to find out mu under any particular condition, we simply write it in this particular terms, and from here we know that d of mu minus mu 0, that is equal to RT d ln F by P, which is equals to V minus RT T by P dP. And now what we can do, we can integrate this equation from what state? F by P equals to 1. Under what condition that happens? When P equals to 0. So, therefore, in this particular way if we write, then in that case we find that on integrating this, we can write it down as mu minus mu 0, this is equals to R T ln F by P, which will be equal to 0 to P V minus R T by P dP. So, therefore, this now becomes the defining equation for mu, or if you say it is, this becomes the defining equation for the fugacity, and this particular ratio F by P, since it is very frequently encountered. So, this is given some particular notation phi, and it is known as the fugacity coefficient. And since we know fugacity under some conditions, so therefore, it was felt that phi naught replace mu with fugacity, and just we can write down all the things which were written in terms of mu just in terms of f. And for such a condition, we find that Fi alpha will be equal to Fi beta for any particular component I, if the component is pure, and if the component is in solution, then naturally we denote them with a cap just to show that this particular F of component I corresponds to the existence of I in some particular mixture. And therefore, the entire problem of determining equilibrium in terms of chemical potential boils down to finding out the fugacity of that particular component in the particular mixture, right. So, therefore, suppose we have some particular mixture, and in that particular mixture, if we find that we would like to find out F. So, therefore, if I can insert one more slide and I can show you. So, therefore, in this particular case, what we find is that our entire problem then boils down to finding out the fugacity of the component I in, say, the alpha phase, and to find out the fugacity of the component I in the beta phase, where what is Fi, say, in the vapor phase or in any particular phase, this is nothing but equals to phi I y I p, right. Because if you recollect in the last slide what I had written down, for a pure component we had written down that R T ln F by P, that was equals to V minus V minus R T by P dP 0 to P. Yeah. So, therefore, this is the equation, and if I have to write this equation for component I in a mixture, then in that case, or this can also be written as R T ln phi for that component, and if it has to be written down for a mixture, then it becomes R T ln phi I bar, which is equals to R T ln F I by P I or Y I P, whatever way you can write it. This is equal to 0 to P. In this particular case, this becomes the partial molar volume, and so therefore, this becomes the equation. So, therefore, in order to find out F I for the alpha phase, what should it be? F I alpha should be phi I alpha. If suppose this is this I write it down as the vapor phase, then it becomes phi I vapor y I p, and if suppose say this is the liquid phase, then it becomes phi I liquid xi p. So, what do I need to do for finding out FIL and FIV? I need to compute these parameters. Now, for the vapor phase, it can be done. How it can be done? The expression can be obtained from here, and this particular expression we can find this out from any particular equation of state. Mostly for gases we know that they conform to the Amagat's law of additive volume and the Dalton's law of partial pressure, and therefore, the partial molar volume is equal to the molar volume of that particular component. And molar volume can be obtained from any particular equation. It can be a cubic equation, it can be a virial equation of state, it can also be the compressibility factor chart. So, from anywhere we can find it out. But when we try to find it out for the liquid phase, what we find is that in the liquid phase, finding out or evaluating this particular integral is slightly difficult, because we know that this particular the partial molar volume, which is nothing but del V del Ni at constant T p, all the other components have remained constant. So, therefore, this it varies with composition, and this particular variation we are required to know at every pressure starting from 0 pressure to P pressure. Now, this becomes finding out this becomes very difficult. So, therefore, other than a vapor phase, finding out Fi liquid, it is very difficult when component I is in a solution. So, just to eliminate this particular difficulty, an ideal solution model has been assumed in the liquid phase, which states that the molar the partial fugacity of component I in the liquid phase, it is proportional to the composition in the liquid phase and the pure component fugacity of that particular component in the liquid phase, provided the Fi0 and the Fi are evaluated at the same conditions of temperature and pressure. Now, this particular model, this is known as an ideal solution model. And in this particular, usually to find out FIL, we use this particular ideal solution model, where the pure component fugacity of I in the liquid state, if you would recall, this was equal to the saturated pressure into the fugacity coefficient of the vapor in equilibrium with the liquid into a Poynting correction factor, which arises because the pressure is far removed from the or rather this is not required, since I assume Vc is equal to constant. So, therefore, the Fi0, it is a summation, or rather it is a product of these three things, right. So, therefore, at low to moderate pressures, what do we find? This is almost equal to 1, and this becomes equal to 1 because P is close to P saturated, Vc is constant. So, therefore, at low to moderate pressure, what do we find? At low to moderate pressure, in that case, we find that for a vapor liquid equilibrium, phi I V into Y I into P, this is equal to xi Fi0, provided, or in other words, for low to moderate pressure, this becomes xi Pi saturated, this also becomes equal to 1. So, therefore, we get the Raoult's law at low to moderate pressures, and the xy data are generated from this particular equation. If you know any particular x, what is the y in equilibrium with that x? The y in equilibrium with the x, it corresponds to xi Pi saturated by P, and this Pi saturated we can find it out either from the Clausius-Clapeyron equation, or we can find it out from the Antoine equation, and we can construct the different curves corresponding to VLE data, which we are going to discuss in the next class. Thank you very much.